Logarithms might seem daunting at first, especially when you encounter them frequently in advanced math like calculus. But once you grasp the concept, they're actually quite straightforward and incredibly useful. So, let's dive into the world of logarithms. So let's say we have the exponential equation 5 to the power of 3 equals 125. We already know what this means. It's just 5 times 5 times 5 equaling 125. But let's analyze what each part of this equation really means. The 5, that's just the base of the equation. That's what's being multiplied. The 3, that's how many times we are repeating the base, how many times the base is going to be multiplied by itself. And the 125, that's just the exponent applied to the base, or the result. Now, logarithms are just essentially a different way to talk about this order. Let's rewrite the original equation, 5 to the power of 3 equals 125, in logarithm form. In logarithms, you aren't solving for the quote-unquote result, as we do in exponents, but, well, for the exponent. We want to know how many times we are multiplying the base to get a result from an exponent. The way we would write this is by writing the 5 as a subscript and the 125 as the argument. What this is basically saying is if we start with 5 and we want to get to 125, how many steps of multiplication of 5 by itself will that require? How many times will 5 repeat itself? And the answer is, as we know, 3. Let's get into some of the uses of logarithms because there are many in nature. When I first learned of the function, I thought it was quite random, but in reality it's far from that. We can begin by examining a graph of a logarithm. Here I have graphed log base 10 of x. Notice this section here. X is relatively small, but there's a huge amount of growth before it kind of begins to level out. And this leads us to one of the main uses of logarithms, to describe the very, very small. One super cool use of logarithms is in chemistry with pH. pH is a measure of acidity, which is just the concentration of hydrogen ions in a solution. Now, hydrogen ions have a very significant effect on the chemical nature of solutions, but there's a problem. Relative to most numbers that we're used to working with, hydrogen concentrations are very, very small, like the number 0.0000000000964. Comparing numbers this small becomes tedious for humans to analyze, so instead, utilizing the fact that log functions undergo dramatic change when x is super small, we can figure it out. So to find pH, what you do is actually take the negative log base 10 of the hydrogen concentration to get the pH. So for this number, the pH is about 9.02. Big numbers like these are much easier to understand and compare, which is why we use logs to make our lives easier.